Now that tool that it uses may be an electron beam. That tool that it uses may be a beam of light. It could be a water jet. There are a lot of things that tool could be. If you change something, it could be cutting, turning, boring, and you'll often have probes on there for measuring things. Probes, actuators, transducers, stages. So, okay. Now, a precision machine tool is a machine which uses any variety of tools to controllably, repeatedly, accurately, that is, with tolerable uncertainty or low uncertainty, change the physical shape or other intrinsic state parameter of a workpiece. And that means milling, grinding, boring, turning, lithography, E-beam, optical, imprint lithography, iron beam machining, electrical discharge machining. All of these have something in common. They move things around and they use a particular tool to change something. Common mechanics are positioning stages and linear and rotary axes. They're constrained, they're controlled, and they're directed. For the high precision machines, they're constrained and controlled. Okay, here's the graph I want to show you. This is a very old graph, by the way. Maintained pretty good. This is from 1983. Taniguchi, who incidentally coined the phrase nanotechnology, where he was the one who coined the phrase. We've heard a lot about that. He talked about machining. And nanotechnology for him was machining. You have normal machining, which over the years, the tolerances were decreasing, and you had precision machining and ultra-precision machining. And if you look at the kinds of machines, you've got just regular machine tools, lathes and milling machines. Then you get precision lathes, grinding machines, lapping machines, honing machines. You've got G-borers, super finishing machines, precision lapping machines. You've got mask aligners, I'm skipping down, optical lens making machines. And you've got down at the bottom, you see diffraction, grading ruling engine, electron beam lithography. The machines are getting better and better. And of course, there's another line, not just with machining things that machine, but things that measure. You also have a lot of different groups of machines that get tighter and taller and taller. This is just to show you that over the years, what's considered ultra-precision machining is getting lower and lower. What's considered normal precision machining, when you move from up there where you got tenths of a millimeter years ago, what would be considered really good now is tenths of a micrometer. It's just normal machining. Precision machining would be like a tenth of a micrometer. So they're getting better. What's the finishes on it? And this is the trend that you will see over the years. So here's the machine that we'll be working on. This is a Monarch machine tool company. Made this. It's called a VMC45, or vertical machining center 45. Can you guys see that up there? Is that better? So this is the machine we'll be working on. It has some of the things, we've got some covers taken off so you can see part of the machine. This is when it was moved in, by the way. Okay. What are the common characteristics of a machine tool? The frame. The basic structure of a machine which provides rigid, stiff support to all its elements. Something that frame usually sits on the floor or on the table. In this case, it's the floor. What are the dynamic elements? You've got motors, ball screws, and carriers, all which move. Those are dynamic elements. And that means they've got some mass, and that mass is being moved, and they have accuracy. They provide the actuation forces, and if it's possible, you want to separate them from the metrology elements. Whatever is doing your measurement, you don't want the forces going through there because it can distort it. There are constraining elements, guideways, ball screws. They limit the degree of freedom, and they maximize the accuracy and repeatability. Now, the metrology elements, which are encoders, scales, read heads, they provide a positioning reference, and they should be separate from the dynamic elements and thermal sources. If you have a glass scale on your machine, on a precision machine, and that glass scale has a motor close to it, the glass scale heats up and cools down with the motor. Now, on any machine tool, the temperature of that motor is going to vary with time. Because as you're performing cycles, you might be doing something on the x-axis for a while. The y motor is cooling off. Then you may go to the y. The y starts heating up, the x cools off. So, how do you predict that if you don't really? We just try to keep the thermal influences away from each other. Here's the dynamic motor. This part right here, this is a motor. So this rotates, and actually it turns this little wheel here with a belt. And this belt is connected, and this little rotor is connected to what's called a ball screw. Now this is a ball screw. See the screw on it here? It's actually like a bearing and a screw combined. I don't have a picture of it, but there are actually ball bearings between the nut and the screw. There are ball bearings, which as you rotate the screw, the ball bearings roll, and it forces the carriage to move back and forth. Now, I know I'm going into more detail, and some of you know all of this, but I'm trying not to miss any bases. So if you have questions, so please feel free to ask. And also on here, you'll see something called a wave. There are guide waves, particularly on this piece here, the two side pieces, keep that carriage traveling straight. It keeps it from yawing. Now, when we first got this machine, the lubrication was clogged up on that. And that stage would do this. So I had to go in and replace the valves, the oiling valves on that. In order to get this correct. There's also the other constraining elements, along with this way here, you see here, there's also the top surface here and the top surface here, which keeps the carriage along a smooth plane, keeps it from doing this. Okay? And it actually keeps it from doing this too. So you get those parallel to each other. There are two ways on there to keep it from doing that. There's another, the quill. This part of the machine tool here that allows the spindle to move up and down. This part here allows the spindle to move up and down. We're going to see this in the lab, hopefully today. This moves up and down. Inside this, it rotates. And there's a rotational bearing in here that allows the tool to turn. There's also another element. This little box here looks like metal. Inside it is a glass scale. The box outside is to support it. Now, if you notice it, there's a flexor on this side and there's a flexor on this side, which you have to see in the lab itself. And that's so that when it heats up, the case will actually expand, or the flexors will keep the glass scale from any stresses being on it. So there's one flexor. And it also provides a particular point for expansion. Okay, what's the load train? Structural loop. The assembly chain from one machining element to another, which provides the physical support and strength for each element. Now, in this case, you've got carriages, guide ways, clamping fixtures, tool holders, spindles, bearings, and you go to the workpiece of the tool, and there's a chain of physical material to material. Like on our machine, you've got a table that holds a part. That table sits on the ways which are on another carriage. You've got the X carriage sitting on top of the Y carriage. That's called a saddle, by the way. And that sits on the frame. On the other part of the frame, you have another carriage that carries the spindle up and down. So you've got that. Actually, you've got two more, but we're not going to do something about that. But there is a loop all the way through there. There's a dynamic actuation loop. The assembly chain from one machine element to another that directs the forces. The metrology links, the partial paths that lead through the machine elements that provide the positioning reference. You've got this, if you think about it, it doesn't go all the way through the machine, but the particular metrology element in this case will give you the position of a carriage with respect to what it's sitting on. So as it moves back and forth, it tells you what it's doing with respect to the carriage below it. Only in the small loop there. There's a small loop there for each element. These are all tied together in theory. They're not physically linked. You can move one without the other, and you've got a complete metrology loop. So they're separable. And there are also some supporting components. For example, if you're using a ball screw to determine how far you've moved, you use the rotation of the ball screw and multiply by the pitch. But as the ball screw expands, the pitch changes. So that's part of the actuation element that you're using there. So that you have to be careful. It's not ideal. A lot of machine tool builders use it. See if I can do it here. For example, let's look at this. A simple carriage. This is a simple model here. So, for example, here's a tool connected to a spindle. This spindle is mounted here on the frame. It's not moving. And it's here, you've got this frame structure, and down through here, attached to the spring structure, there's a motor and a ball screw. This is a simple drawing. There's a nut that's attached to the ball screw. As this ball screw turns, this nut moves back and forth. As this nut moves back and forth, the carriage moves back and forth. Now this purple represents the weight, what it's resting upon. So this carriage is moving back and forth here, resting on this purple stuff here. And here, this particular piece is called the scale. There are little marks on this scale, and as this moves, there's a reed head that counts the number of marks that moves by. And as it counts those number of marks, it tells you how far it's moved. And typically, the spacing on these marks could be anything from 4 to 20 micrometers, and they usually subdivide. There's techniques for getting subparts here, so it's like 1.5 mark, 1.25 mark. And for our machine tool, the smallest that it registers is 2 micrometers, but we're going to prove that in class. So this is like this. And here's just some of the loops of paths that you'll look through. Typically, if you're looking externally, the center of the scale is going to be stable with respect to everything else. And as it heats up, the scale moves out this way. But then again, if you're on a table, it's mounted to a table that's iron. If this heats up, the table expands too. And so you have 2 competing elements here. Both of them expanding. Which one wins? And if they're balanced, you win. So you got this structural loop. You've got the tool going to the spindle, going to the frame, up through the weight element, to the reed head, to the scale, through the scale, up to the table, over to the part, back up to the tool. And that would be your machine path. And if you were going to do a thermal model, you would want to include all of those paths. You're going to do a great thermal model. I've never seen one done. If there's too many variables, you can't keep control of it when you're trying to do that. Just to let you know it's difficult. By the way, here's the problem with it. I don't want to go through that. So, at this point, I'm going to go through this a couple more slides. So, the tool displacement actually, how do I develop this? What methodology do I use to determine this? First of all, you have to develop a proper mathematical model, which is what I mentioned in the drawing. You have to have a model. And we're going to do that in class. We're going to go over step by step, because I'm going to bore you to tears with some details. I hate to tell you that, but once you work through it, you'll understand why you have to do it. And one of the greatest problems with people who are trying to measure things is they don't know what reference frame they're measuring with respect to. They're never really sure about that. And so they lose out, and they lose information, and sometimes they get really confused because they don't understand that. So use the model to determine the metrology. What don't I know? And that's from the parameters, symbolism, there's dependent, independent variables, there's some controlled, some uncontrolled. But if it's uncontrolled, it can still be measured. Is it bounded? Is it undetermined? I have to specify the instrumentation for determining what instrumentation do I need to find these things out. I have to identify the carriages. And I have to determine the machine coordinates which move these carriages. I have to identify the stacking sequence of the carriages. If you think about it, if I've got 2 carriages, let's say this one moves this way, this one moves this way. Okay, as I'm moving, let's say that this one's rocking back and forth as I move. So I move a little bit, it rocks back and forth. Now, this one moves, but as it moves, the other one's sitting on top of it, so whatever's happening to it is happening to the carriage that's on top of it. And so by building the model, you don't have to try to look at it and figure it out. The model will tell you what happens mathematically. And then you can leave it alone and bring it back and find out what's important and what's not. So it's important to identify the stacking sequence of the carriage and the relative position of the frame, table, and tool. And we're going to associate coordinate systems with each carriage. Every carriage will have its own coordinate system because they can be defined mathematically with respect to each other. So we're going to physically define and relate the coordinate systems at some initial machine state using real machine physical references and states. There's something called the home position, the coordinates. something called a game screen. So you have to incorporate some of the machine knowledge and scope. What is its range, the offsets, and what are its coordinate symbols, etc. You have to develop that. You develop independent variables and dependent variables. And you have, in our case, you have what can you change? Through the command and coordinates. The X machine reading, the Y machine reading, the Z machine reading. There's a W axis too. It can be two rotary axes, which we don't have. We don't worry about that in this. What are the orientation errors, the lateral moving error, positioning error? What is the thermal state of the machine? What are my offsets? I want to go into detail. When we go through these coordinate systems, we're going to see why you need to know those things. They're not difficult to determine. You just need to know that they're there. So, I'm going to determine if I still want to stop at this point. I think I'll stop at this point because I want to take it down to the lab. I'm going to take you down to the lab. And we're going to just look at the machine and talk about it.